Hello everyone. Welcome to SHR Trinity. In our previous video, we explored zero-shot prompting. Today, we advance to the next critical technique, few-shot prompting. In this video, we will cover the foundational interview questions on few-shot prompting, explaining how providing just a single example can drastically improve a model's accuracy and format adherence. Let's get started. Before we begin, if you're looking for practical, industry-oriented training in artificial intelligence and generative AI, SHR Trinity offers a comprehensive 30-hour training program. For complete course details, check the description below. Now let's begin today's interview session. We will now begin with the interview questions for few-shot prompting, Part 3, Applied in Production. Moving on to our next question. How do you implement few-shot prompting in a LangChain or Llama index pipeline?
When implementing few-shot prompting in modern enterprise orchestrators like LangChain or Llama index, you should avoid manual string concatenation. In Python, hard-coding examples into giant multi-line formatted strings quickly becomes a maintenance nightmare. Instead, frameworks provide dedicated abstractions like LangChain's few-shot prompt template alongside an example selector. The fundamental core concept here is separation of concerns. By decoupling your example bank from your actual application logic, you gain the ability to store examples in external JSON files, databases, or vector stores, and dynamically pull them when a user submits a query. Now, let me walk you through the example code structure to see how this works in practice. Notice how we construct few-shot prompt template by passing in examples, an example_prompt formatter, a prefix for system instructions, and a suffix for the actual user query. The example_prompt defines how each individual key-value pair of input and output is rendered. The prefix sets up the general instructions for the language model, while the suffix appends the live incoming input. At runtime, the template dynamically renders these elements into a single coherent prompt string. Using structured prompt managers rather than raw strings proves to interviewers that you understand production-grade AI software engineering patterns.
Moving on to our next question, when should an engineering team transition from few-shot prompting to fine-tuning?
Understanding when to pivot from prompt engineering to fine-tuning is one of the most critical architectural decisions an AI engineering team faces. I always teach my students to treat few-shot prompting as the rapid baseline. When you are launching a new feature, you rarely have thousands of labeled data points, so few-shot prompting allows you to validate task feasibility in hours. However, as your application scales to millions of requests, carrying 5 or 6 heavy examples in every single API call introduces massive financial and latency overhead. You reach a tipping point where fine-tuning becomes mathematically necessary. Fine-tuning updates the actual model weights, essentially baking the required task format and reasoning style directly into the network. This eliminates the need to pass context examples on every invocation, cutting input token counts dramatically. Let's look closely at the example scenario to see the economic impact. Imagine running a high-volume classification system with a 5-shot prompt on GPT-4 that costs $15,000 per month due to token volume. By taking those exact examples, expanding them into a high-quality dataset of a few thousand records, and fine-tuning an open-weights model like Llama 3-8B, you can host that model on dedicated infrastructure for around $2,000 per month. That represents over an 80% cost reduction while significantly decreasing time to first token latency.
Moving on to our next question, how do you systematically evaluate and benchmark few-shot prompt performance?
Evaluating prompt performance cannot rely on subjective intuition or running 2 or 3 manual test inputs in a playground. Senior AI engineers treat prompt engineering as empirical software engineering. To systematically benchmark a few-shot prompt, you must first construct a representative ground truth dataset containing real-world edge cases and target outputs, typically around 100 to 200 validated test items. Once you have this golden dataset, you run candidate prompts through an automated execution pipeline and evaluate the outputs against targets using scoring metrics like exact string matching, embedding-based semantic similarity, or LLM as a judge evaluators. Consider the practical example of using evaluation frameworks like RAGAs, Braintrust, or Langsmith. Suppose you want to decide whether adding 2 extra examples to your prompt justifies the extra token cost. You configure your evaluation harness to run candidate prompt A, which uses 3 shots, and candidate prompt B, which uses 5 shots, across the entire 200-item test suite. The framework automatically scores both runs across metrics like accuracy, faithfulness, and format compliance. If the 5-shot prompt only yields a 0.5% accuracy gain while increasing latency by 40%, the data clearly tells you to stay with 3 shots. Automating this in CI/CD ensures that prompt updates never break production performance.
Moving on to our next question, what is example ordering sensitivity, and how do you run permutation testing?
Large language models are remarkably sensitive to the exact order in which few-shot examples appear in a prompt. This phenomenon is known as example ordering sensitivity. Because transformer architectures utilize positional embeddings and exhibit intrinsic recency bias, an example placed right before the user prompt often exerts a stronger influence on the generation than an example placed at the beginning. To optimize this without adding more tokens, engineers run permutation testing. Permutation testing systematically evaluates every possible ordering of a fixed set of $and examples against a validation benchmark dataset. Let's walk through the example to see how this operates mathematically. If you select 3 highly representative examples, there are $3, or 6 total unique arrangement permutations: 1 2 3, 1 3 2, 2 1 3, 2 3 1, 3 1 2, and 3 2 1. You execute your evaluation dataset against all 6 distinct prompt configurations. It is common to see accuracy vary by 10 to 15% purely based on sequence ordering. Once the test completes, you select the permutation that scored highest on your evaluation metrics. This simple procedure allows you to maximize performance for static prompts entirely for free, without increasing token usage or adding model latency.
Moving on to our next question, how do you handle tasks with ambiguous or multimodal acceptable output formats?
When building production AI applications, one of the biggest challenges is dealing with tasks where the answer could be formatted in multiple valid ways. If a model generates free-form, unconstrained responses, your downstream software parsers, API endpoints, or database ingestion scripts will inevitably break. To handle this ambiguity, we use few-shot prompting to anchor the model strictly to a single, canonical output structure. The technical mechanism at work here is pattern matching. Language models are fundamentally sequence predictors. When you present them with multiple consecutive examples that follow an identical structural pattern, the model's conditional probability heavily favors adhering to that exact pattern in its response. Look at the real-world example provided. By supplying 3 sequential examples formatted rigidly as status, approved/denied, reason, 1-sentence explanation, you teach the model 2 critical constraints simultaneously. First, it must categorize the decision into binary status values. Second, it must restrict its explanation to a concise single sentence separated by a pipe delimiter. This eliminates conversational preamble like "sure, I can help with that," and guarantees that regex or string splits in your backend code extract the status and reason reliably every single time.
Moving on to our next question, how is few-shot prompting used for code generation and internal style enforcement?
Out-of-the-box language models are trained on public open-source code repositories, meaning their default output reflects general public coding patterns. However, enterprise software engineering teams enforce strict internal coding standards, proprietary design systems, and custom SDK abstractions that public models have never seen during pre-training. If you ask a model zero-shot to build a feature, it will generate generic code that fails internal code reviews. We solve this by using few-shot prompting as an in-context style guide. By placing 2 or 3 exemplary code snippets into the prompt, we demonstrate exactly how our engineering organization expects code to be written. Let's walk through the purpose of the React component example. Imagine your company built an internal UI design system with proprietary components like primary button and custom state hooks like useAuthSession. In a zero-shot prompt, the model would output standard HTML button elements and generic React state hooks. But when you provide two complete few-shot examples showing components importing from at enterprise/UI and utilizing UseAuth session, the model learns the context pattern immediately. It generates new code that perfectly matches your team's internal architecture, imports, and error wrappers, significantly cutting down refactoring effort during code reviews.
Moving on to our next question, what are the financial and token budget implications of 5-shot prompts at scale?
While adding few-shot examples consistently improves task accuracy, it comes at a steep financial and performance cost that engineers must calculate before pushing code to production. In high-throughput architectures processing millions of monthly calls, input tokens dominate your cloud API expenditures. Every single example added to a prompt increases the input payload size for every request across your user base. This doesn't just inflate your monthly bill, it also increases time-to-first token latency because the model's self-attention mechanism must process a longer context prefix before generating the first output token. Let's step through the cost breakdown in our example calculation to appreciate the scale. Consider an application handling 50 million requests per year. A zero-shot prompt averaging 200 input tokens at standard cloud API pricing accumulates roughly $25,000 annually. If you expand that prompt into a 5-shot prompt consuming 1,200 input tokens per call, your annual API cost jumps sixfold to $150,000. That is a $125,000 budget increase for the same feature. As an AI architect, you must continuously weigh the marginal accuracy gains of extra examples against these operational token costs, ensuring every added shot delivers tangible business value.
Moving on to our next question, how do you use prompt caching to eliminate latency and cost in production few-shot prompts?
Prompt caching is one of the most effective infrastructure optimizations available for production LLM pipelines. In a typical few-shot architecture, the system prompt and a collection of few-shot examples remain completely static across millions of user queries. Without caching, the model provider must reread token li parse and compute self-attention matrix states for those identical examples every single time a user sends a request. Prompt caching solves this by allowing cloud providers to store pre-computed key-value attention states in memory for static prompt prefixes. Let's analyze how this works using the Anthropic example. By adding the cache_control, type, ephemeral, parameter directly to the block containing your 2000 token few-shot prompt header, you signal to the API provider that this content will recur across subsequent calls. On the first request, the provider writes the attention cache. On all subsequent calls within the cache window, the model skips reprocessing those 2000 tokens. Financially, vendors typically discount cached input tokens by up to 90%, and performance-wise, your time-to-first token drops dramatically. It completely eliminates the financial and latency penalties of utilizing heavy few-shot prompts in production.
Moving on to our next question, what is semantic similarity example selection using vector embeddings?
In complex, multi-domain production applications, using a fixed, static set of few-shot examples in your prompt is inefficient. If your system handles diverse user requests ranging from billing issues to technical troubleshooting, a static set of examples cannot adequately cover every scenario without exceeding context limits. Semantic similarity example selection solves this by dynamically assembling custom few-shot prompts tailored specifically to each incoming query using vector embeddings. The technical pipeline operates in 3 distinct steps. First, an incoming user query is passed to an embedding model like text embedding 3 small, converting the query text into a dense vector representation. Second, this vector is queried against a vector store containing hundreds of curated, high-quality historical example pairs using cosine similarity. Third, the system retrieves the top $k most semantically similar examples and formats them directly into the live prompt context. Let's trace the purpose of the invoice cancellation example. When a customer submits a query regarding invoice cancellation, standard static examples about generic password resets won't help the model generate a precise answer. By performing semantic retrieval, the vector engine instantly identifies and injects 3 historical examples specifically dealing with invoice cancellations. The model receives hyper-relevant context, resulting in vastly superior accuracy.
Moving on to our next question, how do you handle few-shot classification when dealing with hundreds of output categories?
Attempting to perform few-shot classification across hundreds of distinct categories in a single prompt is a classic failure mode in AI engineering. If you try to include definitions and examples for 200 or 500 target classes in one system prompt, you exhaust context limits, cause severe model attention confusion, and incur astronomical API token costs. To solve this at scale, senior engineers implement a two-stage retrieval-then classification architecture. In the first stage, we use fast, lightweight vector similarity search to narrow down the massive list of potential categories to a small subset of likely candidates. In the second stage, we dynamically build a focused few-shot prompt that contains examples corresponding exclusively to those top candidate categories. Let me walk you through the practical support routing example to illustrate this flow. Imagine managing a support system with 500 specialized department routes. When a ticket arrives, Stage 1 generates an embedding of the ticket text and performs a vector search against indexed department descriptions, returning the top 5 most relevant candidate departments. Stage 2 then constructs a minimal few-shot prompt containing exactly one example for each of those 5 candidate departments, asking the LLM to make the final, precise classification. This two-stage pattern reduces prompt size by 99% while achieving high classification accuracy.
Excellent. You've completed few-shot prompting, Part 3, Applied in Production. In the next video, we'll dive deeper into using one-shot prompting to enforce strict JSON and XML outputs for API integrations. If you found this video helpful, please like, share, subscribe to SHR Trinity, and press the notification bell so you never miss our upcoming AI interview preparation videos. Thank you for watching. See you in the next video.